The James Webb Space Telescope, JWST, has recently made a groundbreaking discovery by detecting artificial light on Proxima b. This marks the first concrete evidence of a technological signature, potentially indicating intelligent life on another planet. The JWST's MIRI, mid-infrared instrument, is a highly sensitive tool capable of detecting infrared radiation, which allows it to spot distant urban areas and modern facilities across the universe. Its capabilities extend beyond our neighboring system, Proxima Centauri, enabling the identification of artificial light sources and potential extraterrestrial cities across the cosmos. It is remarkable how we can now use advanced telescopes like the JWST to identify vast civilizations within the known universe. The MIRI spectrometer has already achieved impressive results, but even greater advancements are on the horizon. The Extremely Large Telescope, ELT, set to launch in Chile in 2028, will feature a 39-meter primary mirror, offering unprecedented resolution and the ability to peer even deeper into space. We need such technological developments as our curiosity about the universe continues to grow. We are just beginning our journey to explore distant exoplanets, and instruments like the JWST and ELT are essential for detecting signs of life. In addition to identifying artificial light from massive cities or potential extraterrestrial landing strips, the JWST will soon provide us with another invaluable tool: the ability to detect signs of vegetation on distant planets. This marks the beginning of an ongoing effort to refine our search for life beyond Earth, utilizing better instruments and tools until we discover and potentially make contact with other life forms. The detection of artificial light on Proxima b is a significant milestone. For years, scientists have dreamed of studying distant exoplanets so thoroughly that signs of life would become visible. The presence of artificial light on Proxima b would suggest the existence of advanced technology and, consequently, intelligent life. This might sound unbelievable, but the JWST could even analyze human activities on Earth by studying our light signatures. The most advanced telescopes can easily detect the lights of major cities such as New York, Rio de Janeiro, or Beijing, and the JWST sensors can distinguish artificial light from natural sources, like airports, industrial plants, or space stations. The same process is happening on Proxima b, and for the first time, scientists have accurate data on the potential presence of life and the artificial light it generates. This represents a quantum leap in our quest to find life in space. And one day we might even have the technology to send messages to Proxima b, though it would take over 4 years for a response to reach us via traditional methods. However, the future of quantum computing holds promise. Quantum communication knows no spatial or temporal limits, and once we develop this technology, it could enable real-time communication with extraterrestrial civilizations. Back in 2016, researchers were already speculating about how the JWST might analyze the surface of Proxima b. They imagined that the planet's environment might be suitable for life. By 2016, simulations had already suggested that Proxima b, located in the habitable zone of its parent star Proxima Centauri, might support life. These simulations predicted that Proxima b's unique orbit, which causes one side to always face its star, would lead to extreme temperature differences between the day and night sides of the planet. Without an atmosphere to distribute heat, the day side would be scorching hot, and the night side would be freezing cold. However, the presence of an atmosphere could help distribute heat more evenly, creating a habitable region between the day and night sides. This theory has now been confirmed through the JWST's observations, showing that there could be a temperate zone at the boundary between the day and night sides of Proxima b. While it may seem strange to imagine a planet where life exists in a narrow strip between light and dark, this is a possibility we must consider as we continue to expand our understanding of extraterrestrial life. In 2016, scientists were still dreaming of studying the chemical composition of Proxima b's atmosphere, but today, the JWST is able to provide precise spectral profiles of distant worlds, sometimes hundreds or even thousands of light-years away. The JWST has already detected biomarkers like water, carbon dioxide, and methane, and it has made a groundbreaking discovery on the exoplanet K2-18b, where it found evidence of 4 biomarkers in the atmosphere. The more biomarkers we identify on a planet, the more likely it is that life could exist there. The potential discovery of ozone, which is a strong indicator of biological activity due to its presence in Earth's atmosphere, is particularly exciting. K2-18b could potentially be a habitable world, but we have yet to detect artificial light there. This doesn't mean the planet is uninhabited, as we must consider the possibility of intelligent life existing in different forms, perhaps even underwater civilizations. It's important to remember that not all advanced species may use artificial light. Humans only recently began using artificial lighting, but ancient civilizations were already highly intelligent and somewhat automated. The JWST is also capable of detecting plant life on Proxima b, thanks to its design to observe the universe in the infrared range. With its precise and detailed spectral analyses, the JWST provides invaluable data that enhances our search for life beyond Earth. The discoveries made by the JWST are just the beginning of a new era in our exploration of distant worlds, and there is still much more to uncover as we continue to expand our technological and scientific telescope, JWST, has yet to demonstrate its full capacity to detect plant life on exoplanets, but it holds immense potential in our search for extraterrestrial life. We should not solely rely on technological markers and the emissions from highly advanced civilizations. We must also search for planets that could harbor simpler life forms, such as plants and animals. The JWST is capable of providing indirect evidence of plant life by analyzing the atmospheric components and reflected light spectra. This technique, known as the vegetation red edge (VRE), relies on the spectral signatures of plants in the near-infrared range. When light passes through the atmosphere of an exoplanet and is reflected from its surface, distinct patterns in the reflected light can reveal the presence of chlorophyll or other photosynthetic pigments. Detecting these signatures, however, remains a significant challenge. The discovery of VRE requires precise measurements and high resolution, which can be influenced by atmospheric disturbances and the signal-to-noise ratio. While the JWST is designed for such measurements, we are just beginning to tap into its capabilities. Scientists are improving their ability to identify signs of life in space, and we are witnessing an exciting era in space exploration. However, the direct detection of plant life or biological activity will require future telescopes and missions specifically designed to search for biosignatures. One such upcoming telescope is the LUVOIR, Large Ultraviolet Optical Infrared Surveyor, which is designed to investigate the atmospheric properties of exoplanets with even greater precision and detect potential biosignatures like oxygen spectral lines. LUVOIR will be able to isolate and analyze light from exoplanets more effectively than the JWST, as it will cover a wider range of frequencies and conduct more detailed spectral analyses to identify plant or biological activity. Additionally, the upcoming Extremely Large Telescope (ELT) is set to make significant contributions to exoplanet research. Though still under construction in the Atacama Desert in Chile, the ELT will be the largest optical and near-infrared telescope on Earth, with its 39-meter primary mirror. It is scheduled to become operational in 2028 and will be capable of conducting high-resolution, light-sensitive observations, allowing for detailed atmospheric and surface property analysis of exoplanets. The ELT will be able to detect faint signals from distant planets, like the JWST, using adaptive optics to correct for atmospheric distortions, providing sharper images and more precise data. For exoplanets like Proxima b, this means the ELT will conduct detailed spectral analyses to reveal atmospheric composition and the presence of biomarkers like water, carbon dioxide, or methane. The ELT will also use direct imaging techniques to search for potential signs of artificial light or surface features that suggest the presence of life or advanced civilizations. While the JWST excels in infrared astronomy and is located in space, the ELT's ground-based location with its much larger aperture will provide higher resolution in the optical and near-infrared wavelengths, pushing the limits of exoplanet research beyond what the JWST can offer. Another important mission in development is the Habitable Exoplanet Imaging Mission, HABEX, planned for the 2030s. HABEX aims to directly image Earth-like exoplanets and study their atmospheres in detail. Unlike the JWST and ELT, which focus on spectral analysis and detecting biosignatures, HABEX will use advanced optics to capture images of exoplanets. This will allow researchers to examine planetary features such as continents, oceans, and cloud patterns, offering insights into their potential habitability. One of the primary goals of HabEx is to identify exoplanets that resemble Earth in size, composition, and orbit around their stars. By directly imaging these exoplanets, HabEx will analyze their atmospheres for gases such as oxygen, methane, and water vapor. Gases that, if found in the right quantities, could indicate biological activity on these distant worlds. HabEx will also study the development of planetary systems by observing young stars and their surrounding protoplanetary disks. These disks contain the material from which planets form and evolve over time. By studying these processes, HabEx will provide valuable insights into how planetary systems, including our own, develop. In addition, HabEx will investigate the prevalence of exomoons orbiting planets beyond our solar system. Exomoons, like Jupiter's moon Europa or Saturn's moon Enceladus, may harbor conditions suitable for life, and identifying and studying them will enhance our understanding of how common habitable environments might be in the universe. The development of HabEx is a collaborative effort between NASA, international space agencies, and the scientific community. Designing such a complex mission requires expertise in astronomy, optics, and engineering. The telescope's instruments must be highly sensitive to detect faint signals from distant exoplanets while maintaining accuracy in measurements. HabEx will push the boundaries of space telescope technology, incorporating advanced imaging systems like coronagraphs and starshades to block out the glare of parent stars and directly image faint exoplanets. Through its focus on directly imaging Earth-like exoplanets and studying their atmospheres, HabEx will significantly advance our understanding of exoplanetary systems and their potential to support life. The data and discoveries from HabEx will inspire future generations of researchers and expand our knowledge of the vast variety of worlds that exist beyond our galaxy. Ultimately, HabEx represents a significant leap forward in the search for life beyond our solar system and will be a crucial tool in our quest to explore and understand the potential for life on distant exoplanets.